So the next speaker is Cătălin Andrici towards formally secure compilation of verified F-star programs.
Yeah. Thank you. Can you hear me? Yeah. Okay, so hi, my name is Cezar, and today I will talk about how to compile verified F-star code to an ML language in such a way that the compilation is verified and is end-to-end. And this is joint work with some people, with amazing people, and some of them are here, like Cătălin and Abigail in the room, and Théo will join later in the week. Can you hear? Can you hear me? Does that work well?
Do you want me to move it?
Yeah, okay. Okay. I'll keep it here. Okay. Yeah, so let's start with what F-star is. So F-star is a proof-oriented language in which one can write programs. Like if you want to verify a web server, you can write the web server in F-star. We can write a specification, and this specification is written by annotating the code with refinement types and pre- and post conditions. And F-star will check that the web server satisfies the specifications, and if the check is successful, then we have a mathematical strong guarantee that this is the case. And as I said, F-star is kind of designed to be used as a programming language. One should write code in F-star and then extract it to other languages such as OCaml. And this code can be run by itself or can be linked into bigger code bases. And actually, there is a big case, a big example, a successful use of F-star is the Evercrypt cryptographic provider that is verified in F-star and then is extracted to C and other languages. And this is integrated in Mozilla Firefox, the Linux kernel, and the WireGuard VPN. So this is, yeah, how F-star was used successfully. Only that there is a problem with this idea of extracting code from F-star. First, the extraction, the compilation is trusted, but then also the linking with the unverified code is trusted. And this is problematic because if the code is buggy or malicious, like the unverified code is buggy or malicious, it can break the internal logical invariants of the verified code. And this will lead to unsoundness and probably security vulnerabilities. So we basically lose the strong guarantees we got by verifying the code. So what we are trying to do is to propose a compiler that is goes from F-star to ML language, and that we are able to verify end-to-end, and we are able to prove a security proof about it. And we want to do this fully in F-star. And we start by looking at terminating higher-order I/O programs. So by I/O programs, we mean that they can interact with the environment, but they don't have any internal state. And by higher order, we mean that the verified and the unverified code can pass between them callbacks. And this is actually work that comes after previous work. So this is work we published 2 years ago, verified. 2 years ago, we published a verified secure compilation framework for verified I/O programs. And in that work, what we do is that we take refinements and pre- and post conditions, and we convert them into dynamic checks so that we guarantee that by linking with unverified code, it's secure. Right, so we have their end-to-end proof and the proof of security, but that work is missing exactly this piece at the bottom, extraction from F-star to mainstream language like OCaml. And this work is addressing that, so we only have to do this bottom part and start from kind of code that doesn't really have refinements and pre- and post conditions at the boundary between verified and unverified code. So why is this step so challenging? So let's take an example. We take this program that takes as an argument a library that will be unverified. And this program is returning an unit, and it's in the IO monad. And this program is really simple. It reads a message, passes the message to the library. It writes the result of the library. And the way we are going to verify this is by using a trace producing semantics, where for each IO operation we associate an IO event, right? So for read we associate an event. For the library we don't know what it is going to do, so that will be a gap there. And then for the write there will be another event. And basically what we want to do is take this program that's written in F star and compile it to something that looks like this. That's purely syntactic. That is just a syntactic expression. So what's the problem? Well, the problem is that this all happens in F star, and the top program is a shallow embedding. And basically, we want to get out in F star a deep embedding. And there is no way to do this without some kind of meta program being involved. And this is kind of tricky because if, for example, if compilation uses quotation, which will be a primitive, right, and its quotation will be a meta program, then we have to verify this quotation, and then this will involve meta theory of F star, and which it lacks, formalized meta theory of F star, which it lacks, and all of that to have an end-to-end proof. So this is kind of problematic, and yeah, we kind of, I mean, this is why this is complicated. And after reading related work on relational compilation and synthesis from OCaml, we came up with a different technique to solve this problem. And we propose our version we call relational quotation that involves two parts, a typing relation and a meta program. The typing relation is kind of special, and it will define the subset of F star we want to compile. And if you look at the type, it's pretty standard. It takes a typing environment, a type, and expression. The difference is that the type is not a syntactic type, it's a F star type. And then for the value, it's not a syntactic expression, but it's a F star value, which is kind of weird because this is already typed as A. But we'll see in a second how this works. And the fact that we use here F star values, like F star values are closed, right? There is no notion of open, closed F star values. We open them up by using this, like environment passing, right? So here we pass an evaluation environment to this value to kind of mimic opening it. Right, so after we have this type, like the type of the typing relation, we can define its rules, and they are pretty basic. So for false, right, we have false is typed bool, and for yeah, and these are again F star bool and F star false. For variables, it's pretty, it's again pretty standard. We only hear that because we have this evaluation environment and it works like a stack, we take the top of it. And then for lambdas, we have the, if we have a body that's typed as B in a typing environment where we have an A, then we can type the arrow right to A to B, and you see that we take this the argument of the lambda and we put it on the evaluation environment. So this is kind of, it's a bit weird, but it follows the standard typing rules. And actually, to support the IO monad, we define two mutually recursive relations following the typing rules of fine-grained call by value, which was pretty interesting to us to find out. So how do we use this? So basically here it's manually writing the typing derivation for the program that I showed earlier. And so basically we only have to write the constructors, and we don't have to define the some of the types. And basically here, this derivation is going to build a new program that will get unified with the program we want to type. And if f star is able to type check this, it means that it's the derivation of the program we want. And what's important about this derivation is that it captures the program's quotation. Like if we look at this derivation, we kind of can see the syntax of the program. So this is why this is so useful, because now we can see this. So how are we using relational quotation? So instead of using the meta program to do compilation, we use the meta program to find this typing derivation of the program, and this will be in our source language. And then, so basically our source language asks for a program and its derivation, and then it can build its syntax. And this is just projecting out the syntax from this typing derivation. To say a bit about the meta program at some point we are still working on this, but at some point we were able to use just type class resolution to find these derivations. So it should be pretty simple. Okay, so the important ingredients, like what's important about this model is that it allows us to do an end-to-end proof by using the typing derivation and by using the typing derivation. So what are we proving about this, our compiler? We prove robust relational hyperproperty preservation. This is the strongest criterion of Abate et al., which is stronger than full abstraction. And this guarantees that compilation preserves observational equivalence. So this is what full abstractions gives one. Non-interference and trace properties. And we prove this by using a cross-language logical relation. And that relates a shallowly embedded program to a deeply embedded program. So it's kind of asymmetric. And the proof, again, is done recursively on the typing derivation. And what's the most important is that we did not have to do any meta theory of f star. We just have to define this typing relation and do the proofs losing the logical relation. So we are, so to recapitulate, we propose, we are working towards a secure compilation that is end-to-end verified, and we prove strong security criterion about it. And all of this is fully mechanized in f star. And the key idea was to kind of, instead of using metaprogramming to compile, was it to kind of, in the source language, to find this derivation. That was it. Thank you.
So, any questions? No? So I have a question about your meta kind of task. You said that it's quite easy to implement the meta program, taking you from this shallow embedding to the deep embedding. Did you have to modify in any way f star in order to do that, or it's just?
So this is a meta program, right? So we don't. Like, not yet. For now, we did not find any reason to modify f star.
Okay.
F star already has, there is meta f star that offers tactics. So it already has great support for meta programming.
But when we're doing the questions, can the next speaker to set up his machine or a machine? Yeah? Ah, okay. And I mean, you still have to establish some kind of proofs in order to relate both. Were they fully automated?
So the relation between the derivation and the program comes from the dependent type of the typing relation.
Ah, okay.
That says that this is the derivation of the program.
Oh, okay. So it's this typing mechanism that.
Yes.
Okay. Thank you.
So the title says terminating. What would it take to cover non-terminating programs? You mentioned the web server at the beginning, which is typically a non-terminating program.
Yep. So right now we are looking at how to compile Shaolin embedded code, and so basically one will have to kind of pick a monad to do non-termination. So right now the standard is to use I-trees, but I-trees are not supported in F-star, and this is why kind of we didn't look much into that. And yeah.
No other question? So let's thank the speaker again.